Thank you very much for joining. Welcome to the event. You can see here is the agenda proposed for the session, this small workshop. I am Massimiliano Pittore, the coordinator of the project TRANS-ALP, and what we would like to do here today is just to present to the people which might be interested a few insight about the first results of the project, which are relevant for, or might be relevant for practical applications in the near future, hopefully, within the context and the framework of risk assessment. The TRANS-ALP project is a DG ECO funded project which started the 1st of January 2021 and will end at the end of 2022, so in 6 months more or less. So we are let's say in schedule, and the work is still in progress. Nevertheless, we took this chance to we wanted to take this chance to present some of the results, and I think even more to keep fostering the discussion about the potential challenges of storm risk assessment and in general risk assessment when it comes to intense hydrometeorological events in alpine regions. I am co-moderating this session together with my colleague Francesca Borg from EPC, which I would like to introduce. I don't know if you want to use the microphone.
See if also this microphone works. Thank you very much to who is here in presence and to who is connected online. And thank you to DG ECO and the Union Civil Protection Mechanism program that gave us the opportunity to start this project and this international cooperation in the field of civil protection. That is one of the main objective of this program that gave us the opportunity to put together different expertise, different point of view on a same and common problem, that is to protect ourselves and our environment from man-made and, in our case, natural disasters. So it was an occasion to share knowledge, to go behind the state of the art, and now we want to share also with stakeholders and external experts. And the objective of this meeting, as told by Massimiliano, is to enlarge the network and to receive, we hope, feedbacks and further ideas to go on further on this topic to find really usable and effective solution together as supported by the European Civil Protection Mechanism. So, back to you.
Thank you very much, Francesca. So as you will see, or as you are already seeing, we have 3 contributions scheduled for the morning. The first 2 are a joint, result of a joint work of the partnership of TRANS-ALP. And in general, we picked up 3 different areas, thematic areas of the project as a way to present some of the results and also spark a bit more of a discussion. I will then, let's say, after this first part of the presentation, there will be a 15 minutes coffee break, and then the floor will be open to general discussion, questions, and so on. After each set of presentation, anyway, we would like to have a short question and answer time, 5-10 minutes if there is some urgent question. Otherwise, we can also keep, let's say, the questions which are more interesting for discussion for later on. So it's up to you. Feel free to also pose questions directly in the chat of the Zoom session for the people online. We will be monitoring those. And if you want to make a question or make a contribution, make a comment, just let us know. We will monitor the chat and we will give you the floor virtually, so to say. Okay, I think we can get started. And I would like to give the floor to Sebastian Lehner and Alice Crespi. Sebastian is a researcher from the ZAMG, the Central Institute for Meteorology and Geodynamics of Austria. And Alice Crespi is a senior researcher from EURAC Research. Please, floor is yours.
Technical organization at the beginning, so we give time to a few more participants to join online. Number is increasing. As told, the meeting is recorded, so you can keep the camera off if you prefer. For questions and comments, just simply write in the chat or ask, and we will give you the microphone. Okay, new presentation started.
So first of all, good morning, everyone. And I will start present this first part of our workshop. And here we want to present the work that we did for the identification, characterization, and analysis of cross-border extreme events in the Alps under climate change. This work, as Massimiliano introduced, that was carried out together with ZAMG. So first of all, we try to understand how we could identify in an easily way past extreme events. And to do this, we started with the available data that we had for Austria and Trentino South Tyrol. Here we had two, or maybe we have grid data sets of daily precipitation observations at 1 kilometer resolution. And these two data sets, one is produced by ZAMG, it's called Spartacus for Austria, and extend from 1961 up to present. And the other one for Trentino South Tyrol is a bit shortened, so starts in 1980. And then extend up to now. And these two data sets are built by an interpolation procedure of high quality observations that are collected by the regional weather station networks. And these two data sets allow us to have a daily description of the total precipitation that occurred over the area. So we decide to start from there and to use precipitation as a first basis to highlight the most intense extreme events in the past. So and we also apply a very similar interpolation procedure so that these two, let's say, these two data sets are totally comparable. So we started to use, we try to use to start from, as I said, quite straightforward method that allow to extract easily interpretable information. So the first approach that we used was for each day we computed, for each day we computed the total precipitation over the area, so over the entire territory. All the grid points were summed up, and then we turned out with a unique daily time series for the area, and on this we computed the 99th percentile, and we count, or we select the days in which this total precipitation amount was above this 99th percentile. This approach mainly allow us to identify the, let's say, we call large-scale events, because we identify mostly those cases in which the high precipitation values occur over a large amount of grid points. On the other side, then we decide also to integrate this with another approach, quite similar but complementary, that allow also to identify the small-scale events. So in this case, for each day, we computed the 99th percentile specially, so over the entire grid, for each day from the 80 up to present, and then we ranked the dates in which we have the highest precipitation amounts of the 99th percentile computed specially. So we can really pick up just the grid points in which we have very high precipitation amount. At the end, we came up with two lists of events, one for each country, one for each territory, and we analyze such lists in order to identify the most meaningful events in the last 40 years. And then we characterize such events in terms of frequency, seasonal dependencies, distribution, and so on. So here just an example of some of these events that were arranged in a chronological way. And what is interesting to note is that for each of these events we found a kind of proof or validation through newspapers, impacts, reporting on impacts, damage, and so on. And it's also interesting to know that most of these events are then concentrated in the most recent years that we analyzed. Yeah, as I said, then we started a kind of exploratory analysis in order to characterize such events. So here, for instance, just an example, we did this for Trentino, South Tyrol, and Austria separately, also in order to understand if there are some territorial differences somehow. And so, for instance, we distributed or maybe we checked the seasonal dependency on the events, and we saw that most of events occurred in the autumn season. Then we try also preliminary analysis of the frequency, how it changed their frequency over the years, and once again we had a kind of tendency towards the increase in recent years. And we also analyzed the distribution of the daily maximum value that we obtained for these events in order to understand and also to check a little bit the tail of this distribution. Then we also create some scatter plots where on the x-axis we have this daily precipitation maximum, and on the y-axis we have the year of the event. And what is interesting to note is that once again we have the highest intensity that are concentrated in the most recent years of the analysis. So for each event then we have daily precipitation that are gridded of at 1 kilometer resolution that allow then to understand the spatial distribution of values and also to provide further information for subsequent applications. However, besides the intensity of precipitation, we thought that also the information on anomalies could be a very relevant information. And in this, for this, we basically computed the ratio of the daily precipitation of each day of the event with respect to the average total precipitation in the corresponding month. So basically for each event and each grid point, we have the percentage, for each day we have the percentage of, precipitation with respect to the mean total precipitation for that month, that is expected for that month. And in this, based on the anomalies, we are able so to assess at which extent an event can be considered exceptional at each specific location, and then we can even better compare events that occur on different areas, in different climate conditions, and also in different seasons. So for this list of events, we did the same, and so we have a kind of harmonized archive of gridded information. So as I said, both intensity and anomalies for the area of Trentino, South Tyrol, and Austria. And it's also interesting to know that in most cases, as I said, the two data sets, even if they were computed separately, independently, they were completely comparable and integrable. So what we want to do, or maybe in order, if we have this archive of information for each event, each of this, let's say, package of event can be used to extract information. So for instance, here just an example for the storm via. Here we can extract the information for the area of interest, so in this case Trentino South Tyrol, and here we can show the daily cumulated precipitation of a specific day of the event, then the precipitation anomaly of the same day, and this data can also be integrated based on the analysis and aims with other information that could be available for a specific event. So here just an example of the hourly average wind speed of a specific moment of the event that was retrieved from another data set available from area analysis. So we want to do the same. We want to provide the same information for each of these events in order to have we call an application-oriented package. So I would conclude here my part. Of course, we know that the use of daily precipitation at starting point, it's good, but limit a little bit the ability to identify short but very intense precipitation events that can occur, especially during summer. So what would be useful to have is to integrate this daily precipitation with sub-daily information in the future. And this method also does not consider precipitation persistent events when we have relevant precipitation, not exceptional, that occur over several days and in any case could cause damage. On the other hand, these percentile-based methodologies are flexible and easy to and provide easy to understand information that can then represent a relevant starting point for further application and further analysis for identifying and characterizing events in the past. And yeah, as I said, they could provide stakeholders with practice relevant information on this topic. Now I will leave the floor to Sebastian Lehrer, who will go on with the future.
Thank you. Good morning. So the next step is to look at the hazard set under climate change. And for this, we have basically two approaches. So the first approach, or the first preliminary requisite that we need is that we need some sort of collection of impact data. For this, we compile various data sources that are available in Austria as well as in Italy to form a compiled impact data set that we can then use and intersect with other data to analyze, especially in the context of climate change. And then we have basically two approaches. The one approach is from the large scale side of things, where we look at weather types, we analyze the weather types, and we determine the changes in terms of frequency and intensity for weather types, and especially for high impact weather types, which were the intersection between weather types and damage data or impact data comes into play. And the other approach is a local scale hazard trigger approach, where we look at very localized precipitation patterns and investigate how they change over time. This is a two-step process. So in the first step, we identify so-called hazard trigger patterns, which are basically precipitation patterns over a period of time before event happens or before we have events registered in the impact data sets. And the second step is to derive hazard development corridors, which depict the change in terms of occurrence over or compared between different time periods. So for the compilation of the impact data, we have a couple of different data sets, as I already mentioned, in Austria as well as in South Tyrol. The region of interest you can see in the top plot on the right-hand side, where we basically look at flood events and mass movement events that are cover both regions to a pretty large extent. So Carinthia and East Tyrol in Austria, and South Tyrol from the Italian side. You can also see the seasonal distribution here from events, which is different between the regions, which of course also depends on the sort of type on how the data is gathered, which obviously is not the same in every part of the world, to generalize this. And we have all these different impact data sets, and we harmonize this using a so-called Inspire registry, and we then have a compiled and harmonized impact data set which we can analyze further. So then we want to investigate the impacts of climate change. That means we obviously need climate models. We use a climate model ensemble based under two different projections. So we focus on SSP 126 and SSP 37.0. So the first is the Paris goal, the 2 target degree global warming goal, and the second is a more carbon fossil fuel heavy scenario which is more climate unfriendly. The colors are the same throughout the talk. So the dark bluish color is always the climate friendly scenario, and the reddish color is the more carbon fossil fuel heavy scenario. So the first approach for the large scale weather type analysis, it's basically we calculate weather type classifications based on the COST733 weather classification software, and specifically we use the GWT weather types, which simply enough stands for large scale weather types. And we especially today focus on the GWT7 weather type, which is a weather type that is very similar to Vaya-like storms. In total, from this weather type classification software, there are 18 different weather types classified. And yes, the link to the extreme events is also that we can calculate weather type classification software based on which is based on mean sea level pressure. And we then have, from the approach before, what Alicia presented, the extreme events that are determined by the percentile methods. And we can then obviously also look into the weather typings that were determined for these days, that are determined as extreme events based on the percentile methods, and compare this subset of extreme events with the impact data that we have available. And in fact, we find that we have a large overlap in terms of high impact weather types, and one of those is in fact the GWT7, on which again we focus here today. And furthermore, you can see, you already saw on the right-hand side a very rough schematic on what the workflow for this procedure is like. The weather type classification we intersected with impact data, and then we do the climate change analysis and determine frequency changes as well as intensity changes. And intensity changes are determined based on downscale precipitation data from the climate model ensemble. So I already mentioned the large-scale weather situation like Vaya. So on the left-hand side, you can see here a meteorological plot of a couple of different atmospheric variables. The one I want to put the focus on here are the white contour lines, which is the mean sea level pressure. And on the right-hand side, you can see the GWT7 that was determined by the weather type classification software. And you can see that the main characteristics are comparable, which again, as already mentioned, means that the GWT7 is the via-like weather type situation. Of course, determined was this by just looking at the couple of days where the via storm was active and looking at the determined weather type for these couple of days, which was 7. So the pronounced situation there is that we have a low south of Greenland, we have a low over the Gulf of Genua, but at the same time we have a high surface pressure over Scandinavia. So then we already look at the first part of the results, the frequency changes. I have encircled here the changes for the GWT7, so for the via-like storms, which is the focus for today. You can also see the results for the other weather types, but again, the focus is on GWT7. And what we can see here is in one, again, on the left-hand side, in blue, the climate-friendly scenario, on the right-hand side, the more fossil fuel heavy scenario. And the colors, the bar charts depict the median of the distribution, and the box plots, so the black boxes and the whiskers depict the distribution, and with distribution, I mean the distribution of the climate model ensemble. So what does this chart tell us? It tells us that via-like storms are becoming more frequent, and also that we have a very high model agreement. So for example, if we look on the right-hand side, in the encircled black box, we can see that most of the black box is upwards of 0, which tells us that a large number of all the climate models in the ensemble agree that there is a positive change in terms of frequency for via-like storms. And of course, as one might also expect, we have a more moderate change with the climate-friendly scenario and a more drastic change with the climate-unfriendly scenario. Similarly, we can now look at intensity. For the intensity, again, we use downscale precipitation. In this chart, we can see the mean precipitation for all of the GWT classes. And what we can see here, similarly to before, is that we have a change in the positive direction, which suggests that via storms are becoming more intense. And at the same time, we have a high climate model agreement, a high ensemble agreement, given that almost, or the majority of the climate models in the ensemble are upwards of 0. And again, we can see a similar characteristics that for the climate-friendly scenario, we have a more moderate change, and on the other hand, for the fossil fuel-heavy scenario, we have a more drastic change. Then we look at the second part, which is the local scale hazard triggers. So for those, we combine the compiled impact data that I showed before with climate data that was showed by Alice, which is the Spartacus dataset, which again covers Austria and South Tyrol, so all of our regions of interest. We then use a statistical model to determine precipitation sequences that precede events that are recorded in the compiled impact dataset. And if we have these weather sequences, we can first of all look at the weather sequences themselves and see if we can learn something from them. And second of all, determine the occurrence changes between a historical reference period and a future period under different climate change scenarios. So the hazard trigger patterns are roughly look like this. So what do we have here? In the top left, we always have for each subplot the region of interest. So on the left-hand side, you can see an example for South Tyrol. On the right-hand side, you can see an example for Austria. The two plots on the right-hand side for each subplot, there are just some statistical properties to which I won't go into detail. And on the bottom left, you can always see those weather sequences. So the Y scale is normalized, so they are not that easy to interpret. But basically, what you can read from this chart is the relative contribution of the time dependence of precipitation. So for example, if we look at the very left-hand side to the bottom for South Tyrol, which is for mass movements in the summer, we can see, for example, that we have a couple of days before an event happens, relatively speaking, more precipitation than a couple of days before. But then we have, this is the first component that is shown in blue, but then we have two other components in green and red with suggests additional contributions, especially the red might be important compared to the blue one, because it suggests that there is also a substantial component of pre-moistening that is happening before events. So then the next step is we have these kind of weather sequences that are again determined between precipitation data and impact data that was intersected, and we can then look at the change from between the historical reference and the future. And for this, we selected a couple of random points in our regions of interest, so on the Austrian as well as on the Italian side, and we calculate the number of occurrences of potential events that are determined by these sequences for the historical reference period and for the future. And obviously, if we have the number of potential events, we can then normalize it and look at the projected changes. And as an example here, again for the same parameters, we have on the right hand side on the top only the two regions again, and to the bottom two examples of the historical of the hazard development corridors. So on the left hand side we have the mass movement category for South Tyrol in the summer, and on the right hand side we have flooding for the Austrian region of interest. And generally, obviously, this is only a small subplot of all of the results, but generally the changes of the hazard development corridor depends on the season, on the hazard category and the region. And for this particular example that I picked here, you can see that it suggests that those local hazard patterns might decrease, and explanation for this is also that we, especially in the summer and in Europe, we observe that we have higher persistence in terms of weather situations, and of course those patterns can especially happen if we have, for example, weather situations like fast-moving lows that are moving through a specific region and therefore deliver various amounts of precipitation. And if we have longer lasting weather situations and only shorter changes between well, good weather and bad weather, this is one explanation for why the weather sequences that we investigate here decrease in terms of occurrence. And yes, there are some other combinations that are showing basically no change in either direction or slight increases. And what we can also deduce from these results is that the uncertainty generally is a bit higher for mass movement hazard events than for flood events. And now we're already at the second conclusions. So generally what we saw is that the projected changes are heterogeneous depending on the weather types for the first part of the analysis, but especially for via-like weather events, which was the GWT7, we saw substantial increases in terms of frequency as well as intensity, accompanied with high ensemble agreement, which is also a very important part when you investigate climate model ensembles. And furthermore, we can also see that other high impact weather types, I didn't explain them into detail in order to not overfill the presentation, but a couple of other high impact weather types also either show increases in frequency, intensity, or large spreads, which means that the potential for a large worsening is there. And generally, we also can see what one might have guessed anyways, that the climate-friendly scenario shows much more moderate changes compared to the carbon fossil fuel heavy scenario, under which the changes are much more drastic. And The last point, we also saw that those continuous weather sequences depend on season category and regions, and some might decrease, which is most likely due to the increased persistence of weather situations that we can also observe, especially as already mentioned in the summer and in Europe. Thank you.
Can you hear me? Yes. Thank you very much, Sebastian and Alice. Is there any question from either here or from the online? We have a kudos. Yes, Michaela?
I have a question, Alice, the anomalies, how to pronounce that word. You showed there were like, so red areas more in the east and north of Austria, and then those blue areas in the transboundary region. Does this mean that especially in the Alpine region and transboundary regions that these events will increase in the future? These high precipitation extreme events you selected? Or how can I interpret this plot?
Okay, so what I showed here is just the example for one event. So here I just plot the anomalies for the day on this August 2018. So here just, yeah, this is by chance that the blue area is the transboundary part of the domain, but in other cases, as you can see here, the greatest anomalies, so the highest precipitation amounts are a bit differently distributed.
So this is an analysis of the past. We assume that those events occurred there, but we can't tell in the future. Like you can tell from this analysis that also in the future that especially this region will be more affected.
Well, what I presented here, as you said, was just the analysis for this past events. Probably, as Sebastian presented, you have to integrate this analysis with the analysis on future scenarios. And here, as you know, what we can do now, what we decide to do now is to characterize such events in terms of weather type. So this, as Sebastian presented, this atmospheric conditions that led to these events, and we starting from there to analyze what will happen, and so what we could expect in terms of this frequency and intensity of events. But we did not provide a spatial characterization of the changes here.
Thank you. Is there any other question from the... Okay. I would have maybe one comment and one question. One comment is the fact that we are often somehow thinking of VIA as a type of really exceptional event, and as a matter of fact, that was it. On the other side, if you look at the statistics, and this is only based on precipitation, we see that these events are actually much less exceptional than we would think, because the degrees of anomalousness of the events that we've seen in the last decade that happened almost, if not once a year, but really frequently, they are comparable with the degree of anomalousness of VIA, at least in terms of precipitation. So on the one side, I think we are sometimes, let's say, distracted by the fact that VIA was special also in the case of wind. So this is, and this is a dimension that we are missing a little bit from this perspective. On the other side, if we look at extreme events, irrespectively whether they are in the summer or fall or winter, they, let's say, appear very different each from the others. Like in 2019, it was strong snowfalls. In 2018, it was a strong wind. But the point, I think, to me at least, is that more and more often we have events that in some way or in another stress very much the local communities, but also the civil protection authorities. And that's something where we might have a bit more comprehensive look, not, let's say, singling out single events always, but really thinking in this perspective. And one question to Sebastian is, the hazard development corridors are really interesting, and I would imagine that, I don't know, even the time frame that you chosen, the 7 days before the observed impact, is somehow resonating, so to say, in terms of potential operational application, because it's pretty much the same order of magnitude of, let's say, relatively, let's say, confident weather forecast. Do you think, at which extent do you think these type of results could be in the future integrated into early warning systems or other type of, say, short-term impact forecasting?
I think generally, so from a technical point of view, it would generally be no problem at all. The hard part is really the characterization that those sequences that you incorporate into some kind of forecasting system are really meaningful, if I may word it like that. So that's the hard part. And what we also saw in all of this analysis is that we still have a non-zero noise component, to put it like that. So it's not that easy to extract a meaningful signal out of all the noisy data. And I think that's more or less the big challenge if you really want to integrate it into a forecast system, because obviously if you have an operational forecasting system, you want it to be very reliable, and yeah, that's definitely the challenge there, to go from the climatological perspective to really an operational reliable forecast methodology.
Thank you. That's a very important point. Anyway, striking that, or at least it's nice that only using statistical methodology you really pick up patterns of precipitation which have also, let's say, quite a specific physical meaning in terms of, for instance, of pre-moistening, let's say, territory before release of landslides and so on. It would be nice to understand what the other components, which are maybe not dominating, might tell us in terms of this. And the last question, at least from this point, is did you check, or would be nice at least, how sense would it make to check longer time frames, like 2 weeks instead of 1 week?
We did not look at it specifically. I suppose if you want to investigate longer time frames, you also need to choose a certain set of hazards, or not hazards, but weather situations, such that you can verify this analysis, because this also then is kind of a hard part, because you need a subset that well represents these kind of developments, and that is not that easy to establish, especially on the local scale that we look at here, because of course if you look at very long time frames, for example 2 weeks, weather systems already move a large part during the 2 weeks, and because of the nature of the methodology that we look at very localized precipitation patterns, you might get very much overlapping signals from very different systems, and yes, I mean, it's an interesting point, but there would definitely need to be some kind of methodology to handle all of these intricacies. Yeah.
Great, thank you very much.
Thank you.
So yeah, we are now moving away from like the weather patterns which are related to such high or storm events like Vaya, more to the management side, and we are focusing on cascading effects, like how to identify, map, manage cascading effects of storm-related forest cover change. So like a very specific topic, and we will present some examples from our study regions, which were East Tyrol, and there also specifically we focused on the region in Kals am Großglockner, which was hit pretty hard by Vaja, and also our study region from Italy, where we really would like to show some tools which were developed, which in the future can help to manage these cascading effects and dealing with the natural hazards which can occur from this, like when the protective forest loses, or the protective effect of the forest cover changes. And we also focus specifically on snow avalanches. So, but also give a short overview. Like I said, we will switch quite often during our presentation, and hope that yeah, you will then be encouraged to ask many questions. Okay, so yeah, like I said before, we are now focusing on cascading effects of storm-related forest cover changes, and they are specifically the effects on alpine natural hazards. And just to introduce you to the topic real quick, so cascading effects or coinciding hazards are also referred to as follow-on events, knock-on events, or domino effects. And they can occur as coupled events. That means like simultaneously during the time period of the storm. Here are some examples, like if you have a severe winter storm with high snowfall, avalanches can release immediately during that storm. Or if you have high precipitation in the summer month, it can lead to immediate flooding. Or another example is due to the swerving of the trees by the wind, rocks can release, and it can lead to immediate rockfall. And then on the other hand, there are so-called process change, where the initial event changes the predisposition for further events. And here is an example which we are facing right now in these areas which were hit by Vaja in 2018, where those wind throw areas then was very good breeding material for bark beetles, which now affect the remaining forest, and this can lead to changes in the protective effect of the forest, and maybe in the future to, for example, new avalanche releases from areas which were previously protected by forest, but also due to the changes of the forest cover to following flooding events, or to a decrease in the protective effect against rockfall. I talked already a lot about the protective effect, and I would like to highlight that it's dependent on the forest structure and composition. And of course, during a storm event, the forest cover changes often immediately. So you have these areas which open up, the trees fall down, and often the areas are cleared, and then can, for example, open up new potential avalanche release areas, as well as change protective effects against rockfall. So this is what I said before. So the canopy is changed, but on the other hand, you also have an increase of the surface roughness, like by the trees which fall down and pile up on the ground. The surface roughness is increased due to the downed trees and stumps, and also the root plates which are opened, and this can have a positive effect, for example, on the snow cover distribution, but also on the layering, and provide a protective effect against avalanche releases. So in this work we did together, we identified 6 steps for identifying, assessing, mapping, and also managing storm-related cascading effects, which we would like to propose. And in the following presentations, my colleagues will give some examples to all these steps. So the first one is, of course, to identify the area where the forest has been damaged, which can be done with different methods, mainly by remote sensing techniques from satellite images or manned or unmanned aerial photography. then to identify the potential of cascading effects and the key variables that control it. This is mainly done due to site visits and by field surveys. And then to measure those key variables that may have changed, and from this to assess then the new scenario, like you have this variable which changed, what does it mean for the natural hazards you are focusing on or you identified as a potential cascading effect in the area that was affected by the storm damage. Then, like a management scenario could be to develop new mitigation plans based on this new state of the system. And at the end, to also implement monitoring plans and to continue to increase the situation and how it changes, also to be prepared for following future disturbance events. And with this, I'm already done with my introduction, and I would like to give the word to Matthias.
Thank you for your introductions, Michaela. As you have seen at the last slide, there are a few steps to do and what we already did in our project regions. And now I'm going to show you what we did in the past in the region of East Tyrol. So a very, very important first step is to determine new potential avalanche release areas, and in further steps make simulations for runout and deposition zones. And first of all, for that, we have to know where damaged forest areas situate. And the Land Tyrol, so the authority of the federal state of Tyrol, did previous laser scan flights in the past. So we call it a pre-event digital surface model. And then the storm Vaya happened. And we got a post-event digital surface model, and the difference of these both surface models, where you can see the large changes of the vegetation cover. So the wind throw in this case gives us the areas of interest where the wind throw happened or where the forest was heavily affected by the wind throw. So these flights resulted into 2,160 hectares of damaged forest over the entire East Tyrolean area. And nearly about 50% of these, so over 1,000 hectares, could potentially function as a PRA, which is a potential release area in the future. So in the next step, we came from these PRAs to the simulation step and got a new potential avalanche runout zones and deposition zones. We did that with our homemade FlowPy model, which is a mass movement, a gravitational mass movement model as an open source, freely available in the internet. Under this link you can see in this slide. And it is an event-based statistical model, so it's just a few parameters to set, so it's not a physical one. And after these simulations, we just faced a few challenges for the future. For the first, we found out that a possible amplification of the hazard situation due to the increased avalanche runout paths or runout lengths beyond the red and yellow hazard zones defined by regional experts and authorities could happen. So just a quick introduction about the hazard zones. The yellow hazard zone shows kind of the furthest runout of avalanche pressures, which could endanger settlements or main roads. And in this picture, you can see that the current yellow avalanche danger zone already reaches parts of this hamlet in East Tyrol, and also a small part of the main road, which is at the bottom right side, and including the hazard, the Vaya storm, which you can see at the top of these pictures I change now, where a lot of forest got lost. We simulated the new avalanche paths, which obviously reach at least 100 to 150 meter of infrastructures further than the yellow hazard zone shows before. So in the past, we've got just, for example, on this main road, which connects all the hamlets, the yellow hazard zone just reached one curve of this main road, and by our new simulations with new potential release areas colored in the black pixels, a way bigger part of the street could be affected. So there is somehow a big change in the potential hazard of this avalanche on this site. Another challenge we identified was that a new avalanche runout paths and the position zones within settled areas, which could not yet be considered by the official hazard zone, come up now. So at the top or in the upper half of this picture, you can see a yellow hazard zone with the yellow arrows, which indicate the avalanche flow direction coming from a south-facing slope. And after our simulations, we identified, for example, an avalanche coming from a north-facing slope, directly flowing into some parts of this hamlet. And yeah, since these new potential release areas through the Vaya storm just arised in this forest side, it's a kind of a new hazard situation which could not be considered up to now. A third interesting challenge the authorities and all the responsibles could face is that some sensible infrastructures have a sudden exposure to avalanches and associated cascading effects. So in the middle of this picture, we see a sensible infrastructure, an energy supply, and a transformer station. And yeah, as you can maybe already identify here, there's a lot of protection forest on the left, on the west and on the east side of this energy supply. So based on the official Austrian protection forest map, you can see in this reddish color that it somehow protects this infrastructure already, or in the past at least. And yeah, the one and only hazard which endangers this infrastructure at the time or in the past was a torrent. So there is a yellow and red zone for torrents. And since the Vaya storm damaged big areas of forest, of the object protective forest in this right part of the picture, we can see that an avalanche, which we simulated with our FlowPy model, could reach the river, which is highlighted in the dashed magenta line. And in a further step, it could happen that a cascading chain possibly triggers a flood because the avalanche or the avalanche debris may be potentially dams the river which flows beside of this sensible infrastructure. So this is a pretty good example for cascading chain, which is possible because of VIA, which was the initial event. So this was 3 examples now we identified in the past weeks in the frame of this project or in our work for the project. And now I give it a quick overview of the current challenges for the responsibles in East Tyrol, for the practitioners, for the avalanche and torrent control, for example. So just immediately after the event, the authorities implemented technical and bioengineering measures, at least at the most affected hotspots or the most affected infrastructures. Hazard zone plans over entire area of East Tyrol was not implemented up to now, and it's area-wide in general not foreseen because of it's too lengthy and it requires for sure too many human and financial resources. For outdated hotspots where the danger zone plan maybe does not work anymore very well, they make determinations in case-by-case basis. What's the outlook for the coming years in East Tyrol? They say practitioners recognize that VIA actually was just at the beginning of a chain of forest disturbances. And since this season, this year, the bark beetle calamities are massively increasing, and they expect the peak maybe in 2 years in 2024. So currently, the authorities recommend to leave deadwood stems on the sites in the forests to create roughness as transverse obstacles. And in the end, we just, that's now our question to practitioners and the broader audience. Could these adaptation of hazard zone plans, which not happened up to now, become an indispensable tool in the future after all what we expect now because of VIA, bark beetle, and maybe other cascading chains in the future? So that was an overview from my side, and you got
thank you, Matthias. I just pick up very briefly where Matthias left when he said that the authorities now suggest to leave the dead wood in place and to put it on the slope to increase the surface roughness, because of course an increased surface roughness in terms of avalanches disturbs the snowpack and decreases the possibility for avalanche formation, but it can also hold rocks back from releasing or from stopping it earlier on a slope. So this is an effective measure, but of course surface roughness, this increased surface roughness changes over time when the stems decompose. And what we did in this project, within this project, is to develop a method where you can monitor the changes in the surface roughness and also link it actually to the development of the snowpack. So the question is, how can we quantify the surface roughness? We used drone-based remote sensing techniques or structure from motion technology to calculate a point cloud and therefore a digital surface model from these aerial images. And then at the same time, we also measured snowpack properties with different methods to kind of connect these increased surface roughness and areas where it's more rough or less rough to potential effects on avalanche formation in terms of the snow stratigraphy, meaning the layering of the snow, and if potential weak layers, which are connected to avalanche formation and release, can develop over a certain area. And we proposed a directional roughness index. This is still work in progress, but we are at a good stage. And what does that mean, directional roughness? This means the roughness in the direction of the slope of the fall line, because this is important in terms of avalanches. If trees are lying downslope or in the opposite direction, and to connect this then to the snowpack. And like you can see here, this is not a windthrow area, but from an avalanche damaged forest where most trees are in the direction downslope, obviously falling. And so also our roughness index points into that direction. And from like a management perspective, you can think about when the trees are piled on top of each other downslope, and you have like areas where they may be piled high, but they are clumped together, then the snowpack can build up very easily and fill those areas in between the stems, and then maybe create potential avalanche release areas. But there are also areas, it's pretty small, I think we highlighted it there in the red, where you see a low surface roughness, of course, on the road, but just next to it there are also some of these arrow pointing in the opposite, or like the transverse direction, thank you, where you can expect a higher protective effect. But we will see what our snowpack observations also show in this term, and the goal is to really develop an algorithm, or it is already like a custom-built algorithm, but to validate it and to calibrate it, that it can be used regularly with a quite like easy and not so time-consuming techniques, that you can come back to those areas after a certain years to see how the roughness changed, how the direction of the trees changed, and identify areas where you need to focus management options or interventions more easily. And yeah, this is still work in progress. We hope we can finish that, but this could be one tool to include also surface roughness into determining potential avalanche release areas, which we did not so far. So with this, I would like to give the word to Fabricio.
Good morning to everyone. I'm Fabricio Talavini from the Araba Avalanche Center, and together with the colleagues of mine, Roberta and Matteo, we tried to approach this work trying to give concrete answers to the needs of the civil protection authorities. And we started from what we have learned from our previous experience in cascading effect, that for us was the cascading effect after the Vaya storm. As technicians from the Araba Avalanche Center, we were involved both in the data collection after the events and the data collection surveys, and also for the avalanche risk analysis. And we work in cooperation with the civil protection authorities in order to carry out some specific civil protection plans. But to do that, we faced different problems. And so we used the TRANS-ALP project in order to try to find out the way to solve those problems in order to speed up the decision-making process. So starting from the collection data, in the day immediately after the event, a lot of technicians from different organizations in our region went on the field. They tried to collect data about their own topic. They were focused just on their own topic. there was not a very good coordination between these offices. And for instance, there were some colleagues of mine of other offices that were collecting data about floods. Other colleagues from the forestry department were just collecting data about the damaged forests. And other colleagues of mine took some data about the damages of the infrastructure. I was personally involved because of my background on collecting data about landslides, and also with the colleagues of mine of the Arab Avalanche Center, we collected data about avalanches. What is the problem of this different expertise? That none of these technicians collected data about other possible hazard that should be created as a cascading effect after this storm. So one of the needs of the civil protection authorities was to have a very friendly user data collection sheets to be compiled just for one technician in order to collect as much data as possible that should be analyzed in the post-processing phases later on in the office. And from a practical point of view is what we tried to do. So you just see some example of the multi-hazard survey sheets that we made that is made in different parts. There is a general part. I mean, you can find on the deliverables of the project all the sheets. All of them are a front and a rear. You just see the front of the sheets. And in the general part, you just have to fill some data about the damages of the infrastructures that have been affected and so on. So there is a part in which you have to collect the data about landslides. It is quite friendly user to compile it. Then another part that takes all the data about avalanches or the potential release area or new avalanche sites that should have been created. And then another part that collects data about the forest destroyed. And the last one is concerning the parameters that can affect the bark beetle spread. And in our vision, this tool should be very useful to face a problem similar of what happened during VIA in the day immediately after the events. Then the other problems we had was concerning the risk assessment. We did it 3 years ago, and together with the civil protection offices, we also did, as I told you before, some civil protection plan specifically to reduce the risk, to mitigate the risk for some villages in the Alpine region. But we faced many problems. And the main problem was that all the decision-making process was made by expert analysis, and it slowed down the decision-making process a lot. So we tried to carry out some GIS tools in this project in order to speed up this decision-making process. And the tools should automatically answer to the question that you see on the slides. So let's start for the first one. We should understand when the avalanches can be detached from. That it means to carry out the potential release areas. So the GIS tool that we developed is just based from starting from the digital elevation model. Then we also can use the slope map, and we know that the avalanches starts in our region between 28 to 55 to 60 degrees, more or less. We also analyze in the tools the shape of the slope, and it is divided if it is convex, concave, or planar. And if there is or there is not a dense ice stream of vegetation, and also there are, I don't have the map here unfortunately, some terrain roughness analysis. All this is just a GIS tools. This is how it works. It doesn't matter. This is the algorithm with all the Boolean logical connections. But what it is important is the output. What you see here is our study area, that is the Cordevole Valley. And the tool automatically indicates which are the potential release areas once we have, of course, an updated version of the land use map. That is the starting point. And as you can see, the tool is quite sensitive. It is capable to understand the difference between the pre-fire condition and the post-fire condition. This is the same place on top of a village and some touristic resorts. The tool is also capable to carry out the susceptibility map. That is a little bit more complex map. It is quite similar to a potential release area, but it is able to discriminate between the potential release area, which of these is much more prone to avalanche occurrence, because it takes in consideration other parameters like the terrain roughness index, the distance of the streams, and so and so. And we should give some, let's say, we should prioritize which of the potential release area are much more important in order to understand which are the much prone to the detach. Once we got the potential release area, we also have to understand what the avalanche runout will be, because it makes a big and a huge difference to know if the avalanche reach or not the vulnerable elements downslopes. The best way to do it, usually, and we also do that, is using some physically based model that, they are quite common used for avalanche services, and but you need a lot of parameters like frictions, like cohesion of the snowpack, like the amount of the snowpack you want to modelize, and so and so. And it's a very time-consuming work, and you can't do it for an entire basin or also an entire region. So we should to know on which avalanches to focus on mainly. So to do that, we developed a new model that is based it is not physically based, but it just takes a morphological approach that, starting from the potential release area, each potential release area, you don't give any information about cohesion, friction angles, and so on. But from each potential release area, you simulate an avalanche that the runout stops when the angle between the release area and the deposition area reach a certain threshold that you decide. And it is decided by an analysis of the previous avalanches occurred on similar paths. Here is the tool. The input data are quite easy. There is a digital elevation model, and you also have the potential release area as an input data. And the important input data we will see later on is the vulnerable elements input data, reclassified as we will see in the next slide. And the outputs are the runout avalanches and map, and also the exposure maps. And here how it works. This is a sub-basin, is the municipalities of Rocca-Pietri in our study area. These were the potential release area, and this is the final result. The runout avalanche map. It's a particular of the same area. These are the potential release areas, and these are the avalanches. So we developed a tool that was capable to simulate at the same time thousands of avalanches for the entire region, potentially. But still, we didn't answer a question, which avalanche we have to focus on. To do that, we should understand which element at risk may be affected by those avalanches. So we tried to make a vulnerability analysis. It is possible to make it in different scale. Of course, if you work on a regional scale, you should reclassify the elements of a topographic map in terms of residential buildings, commercial buildings, and so on. The same thing for the transportation network, I mean the main roads, the secondary roads, and this is a good classification for a regional scale analysis. Of course, if you want to go into detail, but for other purposes probably, you should give much more complex and detailed classifications. The same thing for the facilities and for the population data. And here what we did, we reclassified the topographic map. We used the classification for the large scale, for the regional scale analysis, sorry. Even because it is quite easier to keep up to date. And the final result is what you see here. There is, I mean, the tool automatically crosses the information about the avalanche runout and the vulnerability analysis. And it points out what kind of vulnerable element should be affected by the avalanches. So if there is a main road or a secondary road or a permanent inhabited houses, then a shelter. And it makes a big difference because that is mainly, it's not exactly a risk analysis, but it's mainly an indicator of on which avalanches we should focus on in the next step. So we are almost at the end. So we understood which avalanche we have to focus on. And to do that, of course, we used one more time the physically based model, because those models are capable to give us all the information that we need to understand the real magnitude of the phenomena. That means the flow weight, the impact force, and the velocity of the avalanche. And thanks to that data, we should also indicate different thresholds in terms of snowpack height in order to understand which vulnerable elements along the path of that avalanche should be affected. And this is mainly part of the civil protection plans. You see here there are some thresholds. The centimeters you see is the height of the snowpack on top of that village, I mean from the starting area, the potential release area, and if the snowpack reach that height, the civil protection plans makes some countermeasure actions like buildings to evacuate, roads to be closed, and so on. What I want to point out that this is almost the same result that we had 3 years ago when we made this plan, just with the with an expert-based analysis. But to do that in the whole area, we spent almost 1 year and a half. Using the tool that we developed inside this project, we are sure that we should speed up this process and to reach the same result in a few weeks of work once we have the updated version of the land use map, of course. And that's all from my side. So Michaela wanted to make the conclusion, I guess.
Yeah, it's me again. Very interactive. To wrap this up, we also try to then combine in the conclusions our experience and what we learned from the exchange from the different countries, and especially focusing on transboundary region and managing these storm events, which of course do not stop at a boundary or at a border. And the first one is adapting like existing civil protection tools and passive mitigation measures, like Fabricio showed in his last example, could be an effective and cost-efficient measure and alternative to technical measures. And I put it here also temporally into brackets, because of course we hope and we do everything possible that the forest is growing back and will fulfill its protective effect again in these areas which were damaged by the storm. And for this, for example, an increase in surface roughness, like suggesting to leave some trees in place to increase the surface roughness could also help to provide temporally over a certain time a protective effect. In this time, of course, work with adapted civil protection plans in terms of how to react in a hazardous situation to provide the best possible protection for the life of people and settlements. The second one is the harmonizing of post-event multi-hazard surveying. This was also a very nice example shown by Fabricio when he talked about the experiences they had after VAIA, that it was not coordinated who is collecting what data. It took a certain amount of time to then combine these data to move forward into the post-event management and the recovery phase. And for example, using such easy to apply sheets, which are based on sheets, survey sheets, which are used in practice already, could amplify also the exchange between the authorities. If, for example, we would try to use such sheets as well, that you learn from each other and you ensure that you collect all the relevant data at the right point in time to strengthen then the preparedness response and recovery phase if such events occur again. So that's a big lesson learned from the VAIA event. And the last one is developing like harmonized methods to map and assess those post-wind thrower cascading effects related to natural hazards. We here focused mainly on avalanches, what we presented, but of course it also affects other natural hazards. And we saw that in what Matthias presented and what Fabricio presented was pretty similar from like the point, what you look at, what is your goal, but there are also the exchange between us, between authorities, between the institutions who do these like risk assessments could help tremendously to also then make conclusions in transboundary regions and to learn from each other. And I think TRANS-ALP was a perfect project for this to get in touch and now think about also next steps. So thank you very much. Thanks Fabricio and Matthias, and yeah, we hope for some questions.
We also have a question from the audience online. I don't know, it's for Michaela. So if Marco, do you want to switch on your microphone, Marco Pregnolato, and pose your question directly?
Thank you, Francesca. Yes, my question was relating to, I mean, you spoke about the fact that the authorities suggested to leave that wood on the ground for protective reasons. But I was wondering, when the bark is not removed, I think this could potentially lead to an increase in the diffusion of bark beetle, and just as a cascading effect to the loss of even more forest. So has this aspect been considered?
Yeah, of course. This is a very important question, and I think we have to define in which phase of like the post-event management of these areas we are. Also in East Tyrol, post-VAIA, they did everything to clear those wind throw areas, to remove the wood, to minimize the bog beetle outbreaks. And this is this is the only measure which helps, but we are now in a stage where the pressure from the bog beetles is so high that you can't even keep up with removing all the forest which is infected. You know, the moment where this helps, that you remove the wood and the laying wood, is when the beetle is not in there yet. But also after VAIA, East Tyrol especially was faced with severe storm breakage, I'm sorry, snow breakage. So there were several disturbances affecting the forest coming at once, and they didn't even had the capacities and like the men, the power to remove all that wood in a time where it would have been affected to reduce the probability of further bark beetle attacks. So I think we are now in the stage of it's so-called epidemic bark beetle outbreak, where the pressure from the bark beetle population is so high that it's almost too late to cut all the trees and hope for damming or minimizing the further spread. So I think they now moved to this measure, which I think is pretty effective. And of course, if you remove the bark from the wood, this would be a measure which would further help to increase a further spread. But this is like the difference between an, let's say, epidemic outbreak where you have some smaller areas affected by bark beetles, where it's very effective to cut those trees, remove the wood, remove the bark. But now we are unfortunately in a time where this is almost too late. And I think the authorities do their best to still provide the protection against natural hazards, and this could be an effective measure. I hope this answers your question.
Yes, it does. Thank you very much.
Thank you very much, Michaela and Fabrizio. Is there any other question from the audience here or from the online audience?
The question goes to Fabrizio. You showed at least 2 nice tools you developed for avalanche release areas and runout. I think they are developed inside the ArcGIS.
Yeah.
Are they also available in QGIS?
It is possible to translate them somehow, for sure, but at this moment, we just did it with the ArcGIS. But it is possible to use the same criteria and to do that for QGIS for sure. I mean, probably is something that we should do in the next future.
That would be nice.
Yeah, okay.
I would have a couple of questions if there is no others here in line. One is, maybe, let me see if you are there. Actually, my question is, we have seen that there are strong indications and you have been carrying out a lot of numerical modeling about the potential increase of avalanche hazard due to the wind throat. Is there already, or there can be in the next years or a chance to validate and even observe empirically the difference in the avalanche hazard looking at, for instance, avalanche data, in order maybe even to calibrate better roughness indexes, thresholds, and so on?
So, I have 2 answers to these questions. First off, in order to calibrate the run-out model that we did, we, roughly made the same simulation with the physically based model. We overlapped the results and we checked that the things, at least for concerning the run-out, was almost the same. But for understanding the increasing of hazard, we should remove all the vegetation that is still there in order to increase the roughness, as you did in Tyrol. And for instance, not this winter, but the winter of the last season was very snowy in our area, but no avalanches occurred on the via avalanche sites because of the roughness of the vegetation. What we have seen as a potential release area assumed the fact that you are going to remove that vegetation. It's also a tool that can help the decision makers in order to make some ordinances in which they say, okay, now you can't remove the vegetation, at least since when you have done all the countermeasure works in order to mitigate the risk. But for sure, this approach is going to increase the bark beetle spread. So the politicians or the decision makers have to find the way, the balance between this kind of the risk. What I would like to add is that it depends also on the time of the reaction that you have, because if you think VIA happened at the end of October, that means from the 28th or 30th of October, and the snow covered that area just at the beginning of December. It is not, I mean, even imaginable, even to find out the money to make all those countermeasure works in just 1 month. Can you imagine to realize them? We are still with a lot of area that we don't have countermeasure works right now. So the fact that you leave there the vegetation and you increase the roughness worked, because we didn't have last year any avalanches on those sites. This year was not a snowy year at all. So in the area in which they remove the vegetation, we don't have data. We will see next year, but we are quite confident that in the area without vegetation and without countermeasure works, if the snow will cover all that area, some avalanches will happen for sure, because the roughness is not so high. We will see.
Thank you very much. And I have another question. I don't know if for you or Michaela and Matthias. And the question is, if we leave, or according to the strategy that you are suggesting, to leave most of the wood on the ground, and besides the problem with the bark beetle, is there any foreseeable effect on the increase of wildfire in the future due to this improved amount of fuel? Is this a consideration that should also be accounted for?
So I'm not a wildfire expert, but we recently had this discussion with people who work in wildfire, in the wildfire research field. But I think it could be a possibility, because you have increased like fuel on the ground, which is drying. If you have certain like weather patterns who then can lead to that. From their feeling, what they said is for those wind-throw areas from VIA, which resulted from VIA, that the hazard is not as high, because also it depends where you are. But we do see like fire in areas where we haven't seen before, also in Austria, especially in the spring, when like you have a very dry winter and you have like low snow cover, you don't have the moisture in the vegetation, and also in those dead wood, for example. I think this could increase the fire hazard. But like I said, I'm not a fire expert, but just thinking about it, it depends when many things come together in an unfaithful way, like certain weather patterns and those dried wood on the ground. No.
Okay, no, thank you very much. Okay, I think we can go on. Okay, I hope you have still some energy and patience left. What we wanted to do is also bring in the discussion a bit more the point of risk, which anyway has been already addressed several times, but by the speakers, which to me is already great, because we see a combination of scientific results, but also always, let's say, a great attention to how these results can be and should be taken over by the local civil protection authorities as a way to really bring some improvement to the current practices. And in the TRANS-ALP project, there are activities which are related to risk assessment, and these are actually happening or being carried out now in the next month. So that's very much work in progress. And what we would like to do is to bring in all the different results that we've been seeing so far. Every partner, both jointly or separately, have been doing a lot of things with great value. Now it's time also to start harmonizing all these things together, understanding to which extent those tools, solutions, methodological approaches can be brought into a consistent trans-border framework and be even more useful for practitioners and civil protection authorities. One thing that we wanted to, let's say now, do is to just present a couple of droplets of results of activities related to risk assessment and link those as much as we can to some of the take-home messages that we can somehow distillate from today's contributions. And I will just quickly go through this, but of course, it's not myself. We have a team. I would like to very much acknowledge the work of Catherine Renner, Piero Campalani, and the team of EURAC. But this, again, is also very much a joint effort with all the partners of the TRANS-ALP project. If I can advance. Okay, a couple of things I wanted to just highlight, possibly if there will be time also to be further discussed later on in the discussion, are those acknowledging complexity, going systemic, consider dynamics, considering multiple spatial and temporal scales, and the forward-looking. And let me just go one by one. As for this, I mean, that was really clear also from the presentation of Fabrizio. Actually, your pictures are much better than mine anyway. But what is absolutely clear is that if you think about VIA, but in general, most of the cases that we've been looking at as extreme events in the past decade are complex events where, of course, we never have just one natural hazard, but we have many different hazards, often compounded in the sense that they are really coinciding in time and location, often with cascading effects, which means that there are, let's say, logical and causal loops which are linking those. All of those natural hazards are very much interacting with the societal system, the exposed assets, and this is a very complex environment, a very complex landscape of risk. So one thing that to me could be actually interesting, and that's definitely anyway something which we started doing all together in the project, is to really devote some time to the conceptualization of all the different impacting mechanisms that can take place during such exceptional or maybe not so exceptional events. And we've been using a tool which is already a de facto standard in climate risk assessment. It's called impact chains, but is not yet very much used in the community of disaster risk reduction. But in general, what we aim at is really bringing in all the empirical observations, all the knowledge of the expert, but also what we can really see happening in those events into a consistent logical framework where we can conceptualize what is happening or what can happen and has been observed or what could happen in the future. So for instance, if you think, if you restrict our attention for the time being to two different hazards, like heavy rain and strong wind, which is very often compounded in an intense event, we can see that there are logical causal, let's say, chains where, of course, rain can be, that's trivial, I would say, be connected with the occurrence of pluvial floods. And of course, also to the occurrence of alpine river floods. And the wind, of course, can be directly linked to the wind throws or felling of trees. At the same time, we can see that the landscape of possible impacts can unfold immediately if we think that, for instance, heavy rain can also increase the soil moisture, and this increasing of soil moisture can actually have a positive reinforcing effect on the landslide hazard. and so on. So what we can already see is that already thinking about the very first direct impacts of strong rain and strong wind, we are seeing as how those impacts are spreading around temporally and spatially across the areas which are affected. At the same time, we can say make things even more complicated, but that's not even as complicated as the reality is, and we can link those first level impacts to second level impacts. So if we now start directly from the impacts, which are, for instance, floods or the wind throws, we can already see in line what we can get, like, for instance, road disruption can follow from the wind throws, and this can lead to, for instance, a disruption of emergency services, or can increase the likelihood of a road accident, and so on. On the other side, pluvial floods or alpine river floods can erode bank, and this can lead to other type of impacts. And the very same wind throws can disrupt also power lines, and this can lead to other type of impacts. So, and that's the second level of impacts. And we can go on actually finding a more and more complex set of potential impacts. And the more we go towards, let's say, cascaded impacts, the more uncertain the picture comes, because of course it might be relatively less likely to have a very strong telecom disruption due to power disruption that is actually generated by the wind throws. But as a matter of fact, this has been observed, and this cannot be ruled out, as, for instance, damage to water infrastructure and so on. And this can lead, of course, in different ways to consequences of people or the social systems and so on. This exercise can be brought to the point where we might have something like that, which we call an impact chain, which seems a bit complex, but actually it's much less complex than what we can really think it would happen in reality. It's just a tool for us to conceptualize what can happen, but also what are the factors that are going to be relevant in the amplification or de-amplification of the potential consequences of the socio-ecological systems. And that is, I'm mostly referring to the vulnerability side. So what we can have here is in just one page, and just as a preliminary exercise to say, is a resume, so to say, of a conceptual model of the main hazards that we've been addressing, the main exposed assets which might be susceptible to be damaged and incur losses, the chain, causal chain of impacts that are, of course, or can be observed, and that's also very important, at least a small selection of the factors which can increase the vulnerability of the exposed assets and systems and lead to a higher risk. And as you can see, what I find also interesting is the fact that while impacts are relatively simple and straightforward, and that can be easily retrieved even from, let's say, empirical observation, the vulnerability factors are much more complex, sometimes even difficult to be basically described by numerical or analytical measures, but nevertheless they might play an important role in understanding what are the root causes of most of the damages and the losses that we have seen and that we will see also in the future. And this is also very important in order to devise a larger and more comprehensive set of adaptation and mitigation measures to address this risk in the future. So this is about conceptualization. And I'm just really giving a couple of maybe hopefully food for thought and for discussion. Next point, which is, I think, logically following from this, is the necessity to go further and further into a systemic perspective. And just to exemplify this with a very simple example, I can present the work that we've been doing, that we are doing on the modeling of exposure, looking at the overall TRANS-ALP study area, which is composed by South Tyrol, East Tyrol, and the Gordino Valley. And one thing that we've been doing, because as you have seen in the presentation of Fabricio, what is also very important to risk is understanding what are and where are the exposed assets, which means buildings, people, infrastructure, and the more information we can add, and the more we can harmonize this information into actionable structures, which are also going to cross-border, hopefully, and are really basically providing a picture of what can be damaged and where. This, I think, is of great relevance for risk assessment. So one thing that we did so far is to take a selection of all the possible assets and systems which are relevant, at least for the multiple hazards that can be compounded in a storm, and aggregate, statistically aggregate those assets into a set of cells, which we call a mesh or a tessellation. And those cells, for reasons that I will explain later, are not just squares, but are hexagonal squares, cells. And in each one of those cells, we can provide a number of attributes, numerical attributes, which are providing information on the aggregated number of people, number of buildings, or area covered by built-up areas, and so on and so forth. This is just to show an example of how it looks like the distribution of building area in each of the cells of the model, of the extended model. Of course, the useful or nice thing about this is the fact that this model is covering the whole area, so it's going across Austria and the Italian border, and also across the local border between South Tyrol and Veneto, and is providing a one-stop shop, so to say, for information on exposed assets. We can see resident people, we can see on the right side capacity of schools, which is also an indication of potentially exposed or even vulnerable, let's say, population, let's say, during different type of events. But we can also have information on touristic accommodation, so number of touristic accommodation per cell, or as we see in the right side, we also introduced the information about the protective forest, which can be seen, and that's also interesting to note, at the same time an exposed asset, because if we damage the forest, we lose value, we can incur losses. On the other side, it's also a vulnerability measure, in the sense that the more protective forest we have, the less we are vulnerable to certain type of hazards. And all of those information are already let's say, available for the greater, let's say, alpine area in the TRANS-ALP study area, and are harmonized and aggregated consistently across all the places. Another thing that, and this I think is also a step forward, a bit more of an innovative concept, is not only to think about those this model composed by individual cells, which are providing individual independent aggregation of assets, but also consider the fact that there are infrastructure underlying, like for instance, in this case, we are taking into account road infrastructures, and those road infrastructures, they should not be considered only as physical assets, like for instance, the physical pavement, which can be damaged by a rockfall, but also as functional components, because they have a specific systemic function, which is moving, allowing people to move from one place to another. And what we did, and I won't enter into details, is to take this into account into this model, so that each cell does not only provide information about what is or can be found in the cell, but also how the cell is connected with neighboring cells in terms of road and road capacity. That means that we are basically improving a model by giving a functional assessment role, as well as a descriptive role in terms of physical assets. One thing that we've been doing in order to exploit this additional feature is, for instance, taking into account the potential dynamics of population. We can imagine that the population nighttime is just staying at home, but the daytime population is moving. It can be found in different places. And for doing this, and specifically in South Tyrol, we use data from the local, say, province, in the office of the job market office, in order to understand where the people are commuting, where they are working. And that means that not only we can have an idea about the nighttime population, but also we can basically define a distribution of the potential daytime distribution of population, which is strongly dependent on the commuting patterns of people, which means where the people are working, not only where the people are living. And what is also interesting is the fact that by exploiting the fact that now we have also an underlying functional modeling within the same exposure model, we can also take into account where the population is when they are commuting, so where they are moving from their home to their working place. And this is something that could not be done with a kind of a normal, so to say, standard exposure model if you would not have information on how the cells are connected throughout the road system. And this is a picture which is showing where the main flow of people during commuting will concentrate in the Bolzano area, for instance, but you can see this is available all over South Tyrol. That's, of course, just a first step, takes into account mostly, let's say, the people which are commuting with very simple assumptions, and we are not taking into account, for instance, people going to school, so from home to school, or in other places like shops and so on. But this might come later. This is also our intention to improve the model, because what we can get is something which is taken into account in a much more realistic way, where the exposed population can be in different times of the day, for instance. And this also leads to another consideration, which is at least another suggestion, to consider more and more dynamics in the assessment of risk. We have seen that at the short time scale where the events are unfolding, so over maybe a few hours or even a few days, there are a number of different phenomena which are taking place, which have their own dynamics, and these dynamics might be useful, might be important to be taken into consideration to increase or improve civil protection, let's say, operations. For instance, if we have information about the precipitation pattern, we might be able to simulate let's say, landslides, which are related to precipitation, as we have seen in the conceptual model. And this could also be coupled with the exposure model that we are developing in order to understand with which probability certain roads can be impacted more than others, and how this might lead to further problems. This is something which is more and more feasible, so to say, and this, of course, will be further explored in the next part of the project. And this might also bring another dimension to the conceptualization of risk and the management of risk. Another dynamic, actually a dynamic which I already mentioned, is also taking into account how the different hazards are changing from time to time. This is an example of a result from a companion project. It's another project called the ProSlide, which is coordinated by Stefan Steger, which is here today. And what I'm showing is, say, how a potential threshold for rain-triggered landslides can change from day to day, taking into account the season. Because, of course, depending on the season, depending on the climatological, let's say, environmental conditions, also triggers, in this case, rain triggers can change. And this can lead very interestingly to me, to not only what we call susceptibility models for landslides, but to dynamic susceptibility models for landslides, where depending on the season, depending on the day, and depending, of course, on the amount of precipitation which is observed or even forecasted, we can have a good idea of how the susceptibility to landslides is changing. And this could theoretically also be done for avalanches mutatis mutandis, of course. This, of course, is opening new, let's say, pathways also for scientific, technical, and operational development. For instance, you can imagine that we can theoretically think of putting all these things together, try to understand, depending on the environmental condition or even based on the weather forecasts, how landsliding would, let's say, change or increase activity in a window of a few days even, and then based on this understand which roads might be impacted or disrupted. And with the model that we've been doing, it's already possible to even understand exactly what other alternative routes might or should be taken into account if a road will be closed, and understand if this will bring in critical disruption or not. Just as an example of what could be done in a more dynamic perspective in terms of risk assessment. Another point which I would like to comment is on the consideration of multiple scales. On the one side, I mean, we've seen, for instance, in the work that ARPAV, but also BFW did, that it's now feasible, increasingly feasible, so to say, to have a very large scale assessment of, in this case, for instance, difference in avalanche susceptibility. This has been done on the entire Agordino Valley, but could theoretically be extended to the all alpine areas before or after. And we can already see, for instance, how striking is the difference or potential difference in terms of avalanche susceptibility in the pre and the post VIA conditions. And if we, as you see, we just superimpose the harmonized exposure model to this, you can see how the post-VIA condition is exposing much more inhabited areas. And if you look at the hexagons, which are a black outline, those are cells which are not only inhabited or not necessarily inhabited, but are including primary roads. And you can see immediately that, let's say, the population and road infrastructure, primary road infrastructure, which is potentially exposed to avalanches in the post-VIA framework, is already potentially increasing from the pre-VIA conditions. We are just superimposing right now in terms of, let's say, visual depiction, this information, but of course this can be done numerically, analytically, and can lead to wide area assessment of risk, also with quantitative assessment. Of course, always taking into account that, for instance, now with this type of model, we are not taking into account specific single buildings or single structures, but always taking into account the information aggregated at the cell level, which I think is a good thing, at least at this level, because aggregation increases statistical confidence and decreases also the chance of going too much into the detail, especially when we might be misled by the apparent very high resolution of those simulations. This can be done also with, let's say, more local simulations, as the one that ARPAV did with physical simulation systems. And you see still that even cells aggregated over 250 meters give you a very good idea, even not looking at what are the underlying or where are the underlying buildings, to whether this might or might not be a risk hotspot. Which is for us the most important result, because we are leaving a much more detailed assessment to the Civil Protection Agency, because they have the data and they have the protocols and so on. But the idea is to provide tools and methodologies to really speed up as much as possible the first screening of risk, which can happen over very large areas in a relatively short time, and then let the people, the experts, really focus on specific cases if deemed, of course, necessary. That's just another example, and that's also the example in the case of the simulation, large-scale simulations carried out by BFW in East Tyrol. Again, we can see, let's say, that there is a, let's say, good potential for this type of joint model considerations, and also good potential for later on including as much as possible all of these individual methodologies and tools into consistent even computational frameworks that could bring to the civil protection up-to-date, large-scale, but still probably useful data, let's say, for risk assessment purposes. And last, just a comment that I would like to do, and I will just close here, is related to the necessity to really looking forward, because to me, a few take-home messages from what we have seen today is that on the one side, but of course this we know it, many hazards are not anymore or cannot anymore be considered stationary, which means that they are changing over time scales or few years or decades. We've seen that the probability of events such as VIA might increase in the future, which means that also all the methodology and procedures, protocols for risk assessment have to adapt at a certain point to a changing picture. And not only the hazard is changing, but every time an event the size of VIA happens, and we see that this might also happen more than once in 100 years as we were expecting, those events are completely changing the landscape, but also the risk landscape, and for decades after. And we have seen from what we have been talking about, and also from the conceptualization, that there are complex cascading impacts which can start from a few hour event like VIA with a strong wind throws, but then can trigger processes which are going on for decades and are bringing in very important changes, not only in what we've seen around, but also in the potential risk for social and economical systems, which means that we cannot anymore probably, or I think that's the impression, just looking at what happened in the past to derive let's say, the next civil protection protocols or hazard zoning and so on, but we should also start looking at what might happen in the future, which was never observed in the past. And that means considering also what we call emergent risks, like for instance, bark beetle maybe was not such strong problems 10 or 20 years ago, now might be an emergency. Wildfires in this region have never maybe been considered a major hazard, but might change in the future, also thanks to different underlying drivers, because we might have a very bad somehow combination of impacted cascading impacts like wind throw, let's say bark beetle, increasing of let's say wildfire due to, for instance, drought conditions, reduce the precipitation, which is another thing that is forecasted for the future as connected by climate change. That means that the situation is changing, and in ways that maybe can be difficult to foresee only looking at what happened in the past. And the last point, which I think is also interesting, also to get back to what Matthias showed about this example of potential landsliding, avalanche, potentially damming a river that could then, let's say, flood a power, let's say, converter which is part of the power structure, means that this, I don't know how realistic this is or not, but on the other side, I think it's interesting the potential use of those stories, so to say, or storylines and different narratives to really make sure that in the future, together with the civil protection and all the authorities, we can try and find new ways to explore avenues or pathways for risk, making sure as much as possible that we can spot conditions which could be critical for risk assessment, which haven't been observed in the past or that are difficult to be, say, foreseeable right now. And that was it for my contribution. Thank you very much. This is also closing all the frontal part, which I hope was not too, let's say, tough to follow, since especially for the people online, because it's almost 3 hours. It's a long time. I would suggest we might have, if there are no questions, of course, on what we presented so far, then we can just have a coffee break.
Online, someone want to pose a question? Seems not for now. Yes, there is another question from Marco Pregnolato, so I think we can wait 5 minutes for the coffee break.
Absolutely,
Surely,
yes.
absolutely. So Marco, please, you can pose your question.
Yes, I'm sorry to be that person to postpone the coffee break. Sorry. You said you would elaborate a bit about the choice to go with an hexagonal grid.
Yes,
yes.
You spotted it. Yes, actually, the reason for going with hexagonal cells are several. On the one side, hexagonal cells are, let's say, nicer, or say are more topologically, let's say, suitable to aggregate things. So from the statistical perspective, and also from the what is called the capacity of the shape, so they are closer to, let's say, a circular shape, which has a good properties from the geometrical perspective. Plus, and I can show you this. Figure, they have also nice connectivity with respect to grids, because hexagonal cells, they have 6 different connections with neighbors, which means that I can use directly the structures of which is underlined by the hexagonal cells to integrate the modeling of the underlying road network, which is without losing too much in terms of, let's say, connectivity information and in terms of spatial resolution, which is something which I could not have with a square, for instance, type of cell. And maybe this is technical, but the hexagonal cells and its dual representation in terms of graph, they have very nice topological properties which we can exploit to have a better, more, let's say, stable and computationally efficient description of exposure, and then also go more and more into this functional modeling, which is important for systemic assessment. I hope I answered some of your questions, but of course I will be happy to further discuss.
Thank you very much. Yes, I would have more questions, but please tell me if maybe we should postpone them, or...
I think it's, the questions are related to what we just, what I
yes,
just...
yes.
Please, yes.
Very much. I was very interested in how you characterize the population distribution, because I mean, I've been working on very similar in studies, let's say, and I mean, to characterize the population distribution is quite hard in normal conditions, because, I mean, on a national level, at least, we can only basically have access to ISTAT data, and the most detailed data that we have on from the spatial point of view date back to 2011. So, and also the spatial distribution is not very detailed. So I was wondering where you got the data about population distribution so detailed.
Yes, that's a good question. Thank you. We are lucky that we find ourselves in a very data-rich situation here, especially in South Tyrol, but I would say in this part of the world. And we have also very good collaboration with the local authorities. In this particular case, we used authoritative data, which we have been provided by local authorities, which is on the one side giving us good information on where the people are living, but also where the people are working. And we even have, also, of course, we've been provided this in aggregated form to protect the privacy of the people, but we have information about where people are going from home to work. So we have information about where are the people possibly starting their commuting from, and where the people are actually arriving. So at least for the people which are working, which have an employer here in South Tyrol, and under the assumption that they will every day in the period from 8 to 10, they will go from home to office, which is probably not super realistic now after COVID, but still in this assumption, you have a very good idea of where the people should go, and we used, let's say, classical routing, let's say, procedure to let the people move from one place to another using the drivable road infrastructure. This way we can obtain information about both the static distribution of those people daytime and nighttime, and also the commuting path that the people are most likely to choose when they go from one place to another. That's just a preliminary modeling, let's say, approach. And we are, because unfortunately this approach is relatively difficult to be extended because we need this type of data also from the other countries. That is often actually quite a difficult type of data set to obtain. What we are doing, or actually that is the plan with my colleagues, is to calibrate as much as we can the model in South Tyrol, and then use this model, maybe hopefully using statistical learning and artificial intelligence approaches to extrapolate this model to neighboring regions where we might not have the same type of data set, but where we can anyway have very good assumptions and possibly good performances of this dynamic model.
Thank you very much. I had a last question, but because I was very curious on how you practically manage the double value of protected forests as exposed element and, let's say, protecting vulnerability factor.
Yeah, it was just an observation. We are mainly considering protected forest right now in the model as exposed element. Okay. For instance, we can use it if we want to address how potentially an event the size of Vaya might, let's say, affect the protected forest, and therefore trigger another set of cascading effects, as we have seen. But since the information is over there, there is no reason we should not also use it as, or consider it also from the perspective of vulnerability, susceptibility, so to say. So that's more of a kind of a abstract potential consideration, given the fact that we have this data, and not all the data that we are assigning the category of exposure is only exposure. There is a very strict interlinkage between exposure and vulnerability, and that is just a case which I think is standing up particularly.
Sure. Thank you very much.
Thank you very much for your interest. And I would like also to open the floor to a general discussion or to any further questions that maybe haven't been posed during the meeting. So I really would like to invite all of you to join and contribute to the discussion. Oops.
Thank you, because no, it was something related to the previous presentation, but also an input for discussion. First of all, it's a theoretical question, but okay, if you would like to answer, how much your work was inspired by the hazard of place model of social vulnerability, hazards of place model for social vulnerability by Susan Cutter, if you consider it or not? Okay.
Not at all, but I would be interested to actually go into more details about that.
Because based on this social vulnerability model, first of all, it would be interesting to understand also about the integrated exposure map, also how the surrounding cells are influencing each other. So if the exposure can increase, if a spatial correlated surrounding cell is more or less exposed than the reference of the cell, because yeah, just a matter of thought, but it's because in that model, the spatial correlation of vulnerability is also understood according to the spatial correlation among different spatial units. So every unit is also considered for the influence that can have. For example, if we have an area with a lot of elderly people, a lot of commuters, highly populated, and then an area that is not like this, or an area that is like this, so the situation is different and can have a difference for the risk management aspect. So these reflections can drive a question on: are you thinking to develop a tool, or you already develop it, where you can choose the layer, to choose different exposure dimensions, so something that can be used in an interactive way by, I don't know, a user or the public institution, and how your work, I know there was already a meeting where you discussed it, but how do you think it can be, because I think it can be really useful for risk management purposes, but how practically are you thinking to develop something? Have you already thought about this?
Well, that's a good, that's a very complex, good question. Let's say, what we've been doing so far is relatively preliminary in the direction of, let's say, more integrated risk assessment. The dataset itself has one aspect which is relatively simple and straightforward, because it can be used as a plain, let's say, vector layer with a number of attributes, and those attributes are all coexisting at the cell level with harmonized, let's say, and cross-border, so to say, distribution of the area of the project, which means that you can really load this theoretically into any type of GIS system and use it as a not particularly complicated exposure model, just picking up the layers that you want to use, or you can even somehow use them in more sophisticated ways by, say, doing, for instance, computations on those layers. But that's still actually a relatively simple, straightforward, standard way of using this. Of course, there is an additional aspect, which is this connectivity, which is interesting. And in this case, we think that this might be provided to end users as an additional way of interacting with the system or the model of doing risk computations, because the underlying, in this case, road exposure system is defined over the natural graph induced by the tessellation. And so we project the existing real or actual street network onto a simplified graph. And this is anyway replicating or representing anyway nicely the topological properties of the infrastructure, and then can be used for risk assessment. But the nice thing is that theoretically we could also project other types of infrastructure that have a graph-like structure, such as power network, water, lifelines, and so on. That means that this kind of connectivity analysis that we have shown now only in terms of distribution and movement of people through roads could also be basically associated or accompanied by other similar functional analysis, taking into account power, water, and so on. That really opens a number of possibilities. What you mentioned about the spatial correlation, it's we haven't specifically thought about that. Of course, as you know, in accordance with the Tobler law, there is always a certain amount of spatial autocorrelation or correlation, cross-correlation among the different layers, and this might be object for future research, of course, because, for instance, it would be nice to understand at which extent the patterns of spatial correlation can correlate also themselves with patterns of observed damages or risk, especially the more you go into systemic impacts and the more the structure of the system and not anymore the specific location of the exposed asset plays a role, and cells are actually influencing each other because they are not anymore like individual entities. So that's definitely a lot of potential avenues which can open for the research, and the data is there actually to be used for this as well. Thanks for the question and the comment.
May I? Sorry.
Hello.
Yeah, I'm Marco Brignolato. The question is, I understand that the project is also, tackling the policy-making aspects on risk management or risk mitigation measures, or it will at some point. And I was wondering what kind, if that is the case, what kind of policy instruments are you going to tackle? Because I see I would make a distinction, a strong distinction between those policy instruments that deal with risk mitigation measures and the instruments that deal with emergency planning or the emergency response measures.
That's another very good point, and also a point for discussion. The project is not explicitly dealing with policies, especially related with risk management. And we decided not to go in this direction, but rather to address more scientific and technical components and methodologies that could in a way be helpful for the civil protection authorities in the different countries. But as a matter of fact, as you point out, and as was also quite evident from the discussion, we have very different policies across the different across the two countries, so Austria and Italy, but we have even different policies across the regional borders between, for instance, South Tyrol and Veneto, and also the neighboring regions. So the policy landscape is quite complex, and I completely agree that this cannot be kind of ruled out. But for the time being, within the project, and since we are anyway in an advanced phase of the project, our approach is to try to establish the best connection individually with and also jointly with stakeholders and decision makers and civil protection authorities in the countries, and trying to understand as much as possible what are their constraints, what are their needs, and at which extent we can, based on the information that they want to share and based on the work that we are carrying out on the project, at which extent we can provide them other information, other tools and methodologies. And it's always, at the end, their own decision, of course, how and at which extent to take over what we are producing, and at which extent to include this into their own specific protocols to improve, let's say, the management of risk. But the project is not, let's say, explicitly tackling harmonization, for instance, of risk management policies across border. This might be actually very important and perhaps even a topic of next and future projects activities. But this is a very important point, and I would like to hear if someone else in the audience or here have some comments on this, because maybe this is even a question that, you know, at which extent we as a scientific community we can help improving risk management approaches given this fragmentation of policies, which is also at a certain extent beyond the scope even of our work, but that is really influencing the environment where we are carrying out our work as well.
We have a comment.
I think so what you just said, that is a very, very important point, right? So, I mean, we as the scientific community propose from our knowledge based on our work, our experience, and how we see a certain situation, some tools or some methods to manage the risk. And of course, with having also partners in the project, which are not only focused on research, but also on practice, like ARPAV, you already get some insights how the practice work. But I think using a workshop like today, where stakeholders get informed, get like an overview of what's possible and what not, and in which direction it would go, this should be an entry point to also contact us, right? So not just like digesting the information, go home and say, okay, that was nice. See, okay, maybe this little snippet of what they presented could be actually interesting for our work. So now I'm getting in contact with Massimiliano and ask if we can sit down in a smaller setting and maybe even talk about how these methods can be adapted, that they're useful for a specific question or purpose. And I think this is very, very important to use. So a workshop like today to get an overview of what's possible, of what we identified as the important points, but then also to act because this is what we are here for. Like the scientists want to also make support practice, want to make useful tools and not something shiny which lives somewhere at the internet. So please also, get in contact with us, and then this helps also to maybe plan further projects very specific on specific needs of practice.
Thank you very much, Michaela, for the comment. And perhaps along these lines, if anybody of you in the audience have further questions, you can always contact us, and we will rely, let's say, we will forward any question or even any request for context onto the different contributors. I can just recall that the parties of the project, besides EURAC and the EPC Consulting, are the Federal Institute for Research in Austria, BFW, and the agency, regional agency for environmental protection of the Veneto region, ARPA Veneto, and ZAMG, which is the central office for meteorology and geodynamics, again in Austria. So we have quite some different expertise, experience, capacities, interest and passion, to share, and we will be more than happy to get in touch with anybody to keep up the discussion.
Okay, thank you, Massimiliano. If there are no more comments or questions from here or online, I confirm your invitation to, in any case, to follow the website and keep in touch with us. Various deliverables already produced by the project are available on the website, but of course the idea is to have more of these kind of events in the next few months, more meetings with specific, let's say, stakeholders or just potential network partners and interested parties. So yes, we also shared a signature page where to insert names and email, and if you want, we will keep you informed of what's going on in the second or final part of the project, because the idea is, yes, as you perfectly explained, try now to go on with research activities, to continue on this part of the activity, but also to pass from the theoretical part, from the research and knowledge development to some concrete, small maybe, but concrete improvement for our territories. So more than happy to keep in touch with who can contribute and help us in this final step of our activity.
Great, thank you, and thank you very much, Francesca, for the co-moderation and the support. Thank you again, all the contributors. Thank you for the people that joined here in presence and the people that joined through the Zoom session. We will follow up with at least a message to make sure that everybody has access to the recorded meeting for later use, and will be available for any further information and contacts, and we'll chase you with other events in the next months. Yeah, thanks again, and have a great rest of the day, everybody.